Hi, let us proceed with our design example. We are still dealing with the peg footing subjected to axial load plus the moment acting in both axes. We're going to discuss about the punching shear at the perimeter of 2D from the column face. This is the shear plane perimeters that we are referring to. We need to check first whether this punching shear at perimeter 2D from the column face occur in this peg footing. First, get the dimensions of the peg footing. The proposed size is 2.4 meters and 2.4 meters in both axes. The column size is 300 times 150. You need to first sketch these parameters of 2D and to see whether it is within the peg footing. If you observe the calculation step previously, we have two Ds, one for the major axis, another one for the minor axis. The effective depth varies due to the arrangements of the reinforcement bars. For us to determine the locations of this 2D parameter, we will use the average effective depth. Take 519 plus 507 divided by 2. The D average is equals to 513 mm. 2 times 513 give you 1026 mm. Now you want to check whether this 2D perimeter shear plane is within the peg footing. To do so, you need to first determine the Z1 and the Y1. We have calculated the Z1 and the Y1 previously. Not difficult. Take the width of the peg footing minus the width of the column divided by 2 sides. Same goes to the minor axis. Take the width of the peg footing minus the width of the column divided by 2 sides. The Z1 and the Y1s calculated are given here. Check with 2D. If 2D is less than the Z1 and the Y1, it means that the parameter 2D here is within the peg footing. In this case, 2D is less than both Z1 and Y1. That means this parameter shear plane is within the peg footing, and you will need to check for the punching shear resistance. If it is outside, then you can skip the checking for the punching shear at 2D for the column face. Knowing now the punching shear check will be required, let us look into the solutions for the checking of the punching shear. First, we need to determine the perimeter of this plane. This is calculated by having the width of the column, which is this one, times 2, and then width of the column here times 2 as well, plus a quarter of a circular perimeter times 4. The radius of the circular is 2D. This is expressed in the equation here, giving you 7,000 something perimeter U. Next, you want to determine the area within the perimeter. The area is calculated by getting the area of the column 300 times 150 plus this area, which is 300 times 2D distance. You have 2 of this area times 2 plus this area, which is 150 times 2D distance. You have 2 units of this times 2, and then you have 4 units of the quarter circular area in the radius of 2D. Add up all the areas here. you get AI equals to this. If you find difficulties to find the AI or the U here, always sketch and show the dimensions. Through sketching of this, you can easily solve this. Next, we are interested with this area. Why is it so? It is because the punching shear loads is calculated by the area outside of the 2D parameter multiply the average stress. How do you get the area outside of the parameter? You take the area of the pad footing minus the area within the parameter. That will be the area outside of the parameter. By taking these areas, multiply with the average stress acting on the pad footing. Due to the influence of the moment, there will be redistributions of the stress, leading to some region with high soil pressure and some region with low soil pressure. But in fact, the total shear stress, it will be the same. It is just redistributing from an area to another area. Therefore, you can simply take an average stress, or you can disregard the influence of the moment. Take the average of these two, multiply the area outside of the parameter. You get your total punching shear force equals to 286.5 kN. Next, you will need to determine the shear stress for the punching shear. The punching shear stress here is calculated based on the total shear force, which we have calculated just now, equals to 286.5 kN, divided by the effective area of the shear plane, which is the U parameter times the effective depth. The effective depth, we take the average of the two effective depth, which is equals to 513 mm. And then we need to consider the influence of the moment as represented by the beta. Since we have moment acting at both axes, and the moment for the major and the minor axis are 150, we will need to compute the beta for both the major and the minor axis. Take the MED divided by the shear force, which is 286.5 kN. You have the parameter that we have calculated earlier on. You need to find the K and also the W1. K can be obtained from this table based on the ratio of C1 and C2. How do you identify C1 and C2? We look at the directions of the moment. If the moment goes in these directions, the width of the column parallels to the moment will be the C1, whereas the width of the column perpendicular to the moment will be the C2. Let's say now this is the moment acting on the column in the major axis. 300, it will be the C1, and 150, it will be C2. That's why in the major axis we have C1 equals to 300 and C2 equals to 150. Don't forget about the moment acting in the minor axis. Coming back to this figure. Now the moment is acting in the minor axis. Your shorter span here, it will be the C1. And the longer span here, which is perpendicular to the moment, it will be C2. That means Now your C1 will be equals to 150 and C2 equals to 300. That's why we have 150 and 300 for C1 and C2 in the minor axis. It seems that the C1 and C2 swap in different axes. Having the C1 and C2 determined, you get the ratio between C1 and C2. In the major axis, dividing C1 with C2 gives you 2.0. Whereas in the minor axis, dividing C1 over C2, you get 0.5. Refers to the table here. A ratio of 2 gives you K equals to 0.7. A ratio of 0.5 gives you K equals to 0.45. This is how you get the K. In the case that the numbers fall in between those numbers here, you may do the interpolations to the right number. Having K confirmed, now we will look into the W1. For the punching share of 2D for the column face, the equations for W1 is this. This equations is slightly different from the one for the maximum punching share that we're going to deal with later. We'll use the longer equation. And the equation for W1, it will be on basis of the C1 and C2, as well as the effective depth, which is the average effective depth. And then you get the W1 slightly varied between the major and the minor axis. Substitute all the value into the equation. You get beta for the major and the minor axis. Multiply beta with VED per UD. You get the punching shear stress. This punching shear stress is later compared with the punching shear resistance, which is calculated from the VRDC using this formula. In fact, we have calculated VRDC in our previous calculations, checking for the vertical shear at 1D for the column face. The VRDC mean for the major and the minor axis are given here. You may adopt the numbers, substitute into the formulas to get the punching shear resistance. Or you can recompute the VRDC mean. Just that you need to be careful with the factor K here. Make sure you don't confuse the K in the VRDC mean with the factor K that you use to determine the beta, which ultimately will influence the punching shear resistance. The K that you use for the beta is obtained from table 6.1 in the Eurocode 2 as a mechanism to quantify the influence of the moment to the punching shear load. However, the K that you use in the VRDC mean is actually given by this formula, which is in the functions of the effective depth. Substitute the relevant value into the formula. You have your VRDC mean in the major and the minor axis. Next, you need to compute the punching shear resistance. This VRDC mean appears in the mode of kilonewton, which is the force. It cannot be used to compare directly with the punching shear stress, which is in the units of Newton per mm square. Therefore, you will need to convert the VRDC mean, which is in kilonewton, into the Newton per mm square. By doing so, you need to divide the VRDC mean by BD. This BD should be the same BD that you use to compute the VRDC mean. For checking the punching shear resistance in the major axis, your B will be taken as this. Whereas if you are checking for the minor axis, your B it will be this. Since for this case, a square peg footing is used, both axes will have the B equals to 2.4 meters. As for the D, we use the average effective depth, which we have calculated earlier on in order to determine the 2D. Substitute the relevant values, you get your punching shear resistance as demonstrated here. This resistance shall be checked against the shear stress. The resistance is greater than the VED. Therefore, we know that the punching shear resistance is sufficient.